All right, thank you for showing up. This is EEE 117. This is the asynchronous section for Chapter 9 sinusoidal steady state analysis. So let's go ahead and dive right in. So the last thing we talked about was summarizing phasors in circuit analysis. Kind of have the last page of the Monday lecture is go real quick. Voltage, remember, can always be represented as a magnitude and a phase angle, right? The frequency is kind of thrown away because we just assume the frequency is the same across the entire circuit. So all we need is Vm and that phase angle attached to that cosine. Current is the same thing. We have Im with the phase angle attached to it. Resistor doesn't change at all. It's just a hard ohm impedance. Inductors are the biggest change. This is where you have J x of L because J omega, WL, where W is your frequency. So you do have to find a frequency, and this is in radians per second. So remember that. Multiply by the inductance and throw in that J for the imaginary component, and that's inductors. Capacitors are going to be similar, except X of C is going to be 1 over WC, right? So if you're a power engineer, you're going to burn these two in your brain for the rest of your life. X of C is always 1 over JWC. Don't forget the negative. Capacitor is always negative impedance. The impedance Z can be combined where you have a real part and a reactive part, where R is the resistive part and the JX is the reactive part, where the X could be either X of L or X of C, depending on which element you're looking at. And then, of course, you could have Ohm's law where you could tie everything together where equals V equals I times Z. And this all works out together because this is, at the end of the day, all arithmetic, right? Multiplying V equals I times Z it is vector physics, vector arithmetic, but it's still just something you can do in your basic calculator, right? Like if I use this TI 36X Pro, this is probably one of the best calculators you can get. Yes, you could use a TI-89 and TI Inspire and all that. They're probably better at it, but this one's way faster. I guarantee you I could probably beat you in speed of trying to figure out some simple calculations like this, just because it's less menus to go through. The other big factor is whenever you take the FE exam or the PE exam or any of those state engineering licensing exams, they're not going to let you bring a scientific calculator. A lot of your math courses probably won't let you bring a scientific calculator because it's kind of like cheating because you can program stuff. But this one is cheap enough. It's like 20 bucks. And this doesn't have like built-in memory. So you can get away with saying, hey, I can't, you actually can't cheat with it, right? So it's a really good calculator. I use it every day at work. And I strongly suggest it's a good budget item to make all of these vector calculations by 10 times faster if you do it by hand. Okay. So with that being said, let's go ahead and move on forward. So today we're just going to talk about circuit analysis with phasors. So we know the basics of phasors, but now we got to put it into action. Now, let's do a big picture. Big picture. Why are we even talking about phasors? Well, basically, it makes our lives easier. If you remember, trying to do that resistor, inductor calculations with the e to negative t over tau, r over l time constants, all that differential equations. That's terrible. I hate it. You hate it. We all hate it. Okay. Very hard calculus. I don't like doing anything with inductors and capacitors in the time domain. It's just way too much headache. So much that it's actually easier to go from the circuit analysis directly in the time domain converted to phasor domain, which is what we did last time, right? It's actually pretty easy. You just use drag numbers, right? Drag the magnitude, drag the phase angle, you're done, right? Go from once you have the whole circuit in the phasor domain, then all of your circuit analysis, it's like you're just doing pure resistor-based circuit analysis. You could still use the same Ohm's law, resistor series rules, parallel combinations of or simplifications of resistors. You could do voltage division like you're doing purely resistors, source transformation, source equivalency, Thevenin's equivalent, Norton's equivalent, all the other stuff, right? Node analysis, mesh analysis, KVL, KCL, all that works And the beauty of this is you're taking inductors and capacitors, which used to have differential and calculus involved with it, and just making it into like another resistor. Okay. I like to think about the capacitor and the inductor like a pure resistor, except it has a J component on. So we're going to be playing with vectors, but in my opinion, multiplying and adding and dividing and subtracting vectors is way, way easier than second order differential equations and double integrals and all that bull crap. Okay. So we take a couple extra steps to go to the phasor domain, but now this algebra is very easy. You could use you could again use this calculator, and there's a 3x3 matrix. You could slam in the indexes and then hit enter, and it'll solve even the 3-node equation for you. Okay. Once you have the solution in the time phasor domain, you have to convert it back to the time domain, which isn't that hard because, again, you're dragging those magnitudes and those phase angles back into that cosine function. Okay, you just have to add back in the frequency, which honestly isn't that hard. So basically, going the longabout route, going through the time domain to phasor domain, doing the algebra, going back to the time domain, is still going to be easier than just doing straight up calculus and differential equations. Okay. So let's answer the questions here. What are the extra steps needed to perform phasor calculations? You just need phasor conversions and some algebra, right? Is the steps overall worth it? Yes, because calculus is much harder than arithmetic, even including the conversion process, okay? So the best way to do this is let's go through some examples. Let's show you exactly what's going on. So first off the top, we have a voltage and current phasors right here. We have a circuit and we have voltages and currents everywhere. So we have the source, a current source. We have a voltage across a current source right here. We got 3 branches and impedance. We have capacitor, a RO branch, so resistor, inductor together, and a purely resistive branch. So 3 branches. We want to find current flowing through the 10 ohm resistor. So that's one of the branches. We also want to find the voltage across this inductor. And I guarantee you right now, if you try to do this in time domain, you're going to have, because you have an inductor and a capacitor, it's immediately second order differential equations. You're going to have one node with 4 currents coming in. So it's going to be 4 of those, right? I mean, that's alone like 10 sheets of paper. That's why there's a reason why you never learned how to do this in circuit analysis in engineering 17, because it's going to take like 3 class periods to do. So with that being said, we found a better solution, phasors. So what is the first step? Always step number 1, convert any voltages and currents into phasor form and notation. Because the last thing you want to do is you don't want to half mix time domain and half mix phasors, because your number is going to be beyond wrong. Convert all to one, and then let's do the work. So any sources should get converted. So for example, we have this current source right here. This needs to get converted right here. And the easiest conversion is look at our current. So we have, that might be too much. Give me 1 second. I got a pen, let me use it. So we have 8 as a magnitude. We have a frequency of 200K radians per second, and then we got a phase angle. All we need to do is bring the 8 and the angle over right here. So you have 8 phasor bracket 0 degrees. And that's it. That's all you had to do. It's very simple conversion. You're just literally dragging and dropping numbers. Okay. Next, you got the voltage. So here we're looking at the voltage across this point. Technically, it's across this inductor, right? So that's easy. We just capitalize the V. So just note that, hey, this is now V2. Notice we have that bigger voltage recapitalization. Okay, and lastly, we have the current flowing through the resistor, which is right here. Okay, again, just take a lowercase I, making a capital I, and it's semantics, but it's very good practice to know that, hey, I'm fully in the phasor domain now. Okay, so those are the 3 major components we had to, voltage and current, we had to convert. So we're done with that. Let's go step number 2. Step number 2 is any resistors should get converted, and that's actually the easiest one because resistors don't change. So we have a 10 ohm resistor here we need to convert, and a 6 ohm resistor here we need to convert. Okay. So here we got 6, no change. 10, no change. So we didn't even have to change anything. Okay, so resistors, you just pull that number down. That's by far the easiest one, right? It's also good to note if you have a purely resistive circuit with no inductors, no capacitors, then it's probably not worth doing a phasor conversion because you're not simplifying anything. Because everything is already in purely resistors. It's all algebra anyway. The only real reason why you use phasors is when capacitors and inductors get involved. Okay. But in this case, we have them, and we will be having inductors and capacitors for the entire course moving forward. So we're going to be using it. Okay. But, there's a place and time to use it. If it's just two resistors in a circuit, then it's not worth using phasors probably. Right. All right. Next is let's do inductors. So let's find the inductor in the circuit. Let's use a different color. Inductors, let's call them blue. Nah, let's call them green. Okay, inductors right here, 40 microhenries. That needs to get converted. And it does get a little trickier than that. So here, notice a conversion process. Convert any inductors. Inductors are J times X. Or sorry, the inductor is labeled Jx of L. You need to multiply your frequency by the inductance. Okay. So where do we get W? Remember, it's 200K. We got that right here. So 200K goes right here. So a general rule of thumb is if you need to know what the frequency of the circuit is, look at the source. The source drives the frequency of the circuit. So anytime inside that cosine, whatever is attached to that T, that's the frequency of the circuit. Okay, so that's omega, right? So JWL. So 200K radians in a second, and then 40 microhenries, that's just from the inductor itself. Okay, so that's pretty straightforward. You literally multiply them together, smash them, and you get J8 ohms. Okay, so with that being said, here, we just slap a J8 ohms. So we literally get rid of 40 microhenries, that's not needed anymore, and J8 ohms. Don't forget the ohms, because you want to do that because now you're signifying, hey, I'm just using impedances now. Because now that the inductor is an impedance, we could treat it like a resistor, in quotes, except it's with a J value in front of it. So in the future, I could literally add 6 ohms plus J8 ohms and combine that into a series-based impedance and do resistor reduction. Okay. So step 3, inductors are done. And then step 4, capacitors. Okay. So for capacitors, you have one right here. It's 1 microhenry. Okay. Oh, sorry, farad. So the same thing we'll do it is where do we get the frequency? Oh, sorry, let's go here. Jx of C is going to be negative J 1 over WC. So remember, X of C is negative 1 over WC. The J is just tacked on. Right. And then we just multiply it all out. It should be 1 right here. So where do we get to 200K? 200K is omega, and that gets carried down here. And capacitance is 1 microfarad, self-explanatory. Multiply all that together, we get negative J5 ohms. Okay, so then we come over here, wherever that capacitor was. Let's put that negative J5. Excuse me. And we're pretty much done with the conversions, right? So that top step of going from time domain to phasor domain is now complete. Notice that every single component in our circuit are either capital VIs or some type of phasor. 8 angles 0 degrees is a phasor for the current. 10 ohms, 6 ohms is resistor impedance. J8 is inductor impedance. Negative J5 is capacitor impedance. Now that everything is an impedance, we could treat this like a very basic engineering 17 problem. Now let's do our calculations. So remember, we got 3 things we want to look at. So now let's solve for the main voltage. We're solving for the voltage between these 2 points. Okay, So this one right here. Right. So this bar, this wire, and this wire, what's the voltage across it? Well, the most obvious thing you could do is you have current flowing out of the circuit, right? So this is a current source. It's going to be constant. Remember, for current sources, the voltage will vary up and down. It's really the rest of the circuit is what drives the voltage. So I would go and combine the rest of the circuit, all of this, into one big impedance, right? Once you do that, then it's a very basic V equals I times Z, right? So we could do that. That's not hard. So here we got equivalent impedance of the whole circuit looking in from the source, right? So think of the current flowing this way and coming back that way. So looking into the ball of impedances, we notice the 10 ohm, 6, J8, and negative J5 impedances are all in parallel, right? So let me get rid of this. So think about all this as one giant node, okay? 10 ohm is in parallel with 10 ohm is in parallel with 6 plus J8 ohm, which is also in parallel with negative J5 ohms. Okay, so here we can write 10, double bar means parallel, 6 plus J8, double bar, and then negative 5J. Again, we're treating them like pure, just basic impedance resistors. It makes a lot easier. Now, how do we do this? Well, remember, you take all of your parallel impedances, you add them together, you invert them and add them together. So you have 1 over 10, 1 over 6 plus J8, plus 1 over negative J5, and then you invert the whole thing. You multiply the power -1. Okay. You can literally number crunch this and you calculate it, and you get 4 minus J3. So the whole circuit, looking from the current source, has impedance of 4 minus J3. So then to find the voltage is pure Ohm's law. So notice we have 8. I'm going to get back to this. Yeah. I just want to get the cursor back. Once. I like the green cursor. Oh, well, I can't really help it. I do have it back. Let's use this thing. So here you have V equals I times Z. This is equal to your 8 angle 0 degrees because that's the current from the source. Multiply by your total impedance of the circuit, 4 minus J3 ohms. Number crunch that, you get 32 minus J24. Then you use a calculator to convert that to a phasor, which is 40 angle negative 36.9 degrees. So your total voltage coming from the source is 40 angle negative 36.9 degrees. And that's a phasor. Now, if you want to convert back to time domain, that's easy. Remember, we just take the 40, we stick it right here. We take the negative 36, stick it right there. And this came from the source. Okay, that's it. So we solve for V, all right? I guarantee you, if you try to do this with all these inductors and capacitors in parallel in a time domain, it will literally be impossible or near impossible. You won't be able to do this in paper and pencil. You need some type of computer-assisted program to number crunch all that, okay? But we fit it all into one page with phasors, okay? Next, let's figure out I1. So I1 is a current flowing through this resistor. So we're trying to find a current there. Well, conveniently, we already know the voltage across it, right? The voltage for the source is the top rail, which is a positive voltage, and the bottom rail is negative voltage. So the voltage across the 10 ohm resistor is literally the voltage across the source because they're all in parallel, right? We already know the voltage because we calculated it from the previous one, right? So we have equivalent impedance, but honestly, we probably don't even need this because this is just voltage across a 10 ohm resistor. So here we'll have our V divided by 10. So this is literally Ohm's law, I equals V over Z. Voltage is 40 angle negative 36.9 degrees because we found that from the previous part. And we divide by 10 ohms. So then our current is 4 angle negative 36.9 degrees. So that's your current flowing through 10 ohms, which is I1. And again, we want to backtrack. We could go back to time domain. It's very simple. You take 4, that's your magnitude, stick it in front of cosine, keep our 200K radians per second. That's our frequency. And then slap in that negative 36.9 degrees phase angle. And we're done. Okay. So that's current flowing through the 10 ohm branch. Let's go to the next thing. We want to solve for V2. That's the voltage across the inductor, right? And I can't even think of how I would do this in the time domain. You'd have to you'd have to figure out the current flowing down this branch, I suppose, and then multiply by an inductor. But that's like several differential equations put together. That sounds terrible. So I got a PhD in this stuff, and I can't even begin to think about how to do that. This is why phasors are so good, in my opinion. So how do we figure out the voltage here? Well, let's treat it like a resistor. Do we know the voltage in the top part? Yeah. That's the main voltage from the positive rail, and the negative voltage on the negative rail down here. So we know the voltage between this branch. From there, we could just do voltage division. I know the voltage across 6 ohm and J8 ohm. I want the voltage across the only J8 ohm. That's a basic resistor division, a voltage division circuit with 2 resistors. Okay. So let's go ahead and do that. We got our main voltage, 40 angle negative 36.9 degrees. And remember, voltage division is always taking the voltage you want. So we want the voltage across the inductor. Take that impedance of the inductor, put it on top, and divide by both of the impedances added together. So at the top, we have Jx of L, which is the voltage across the inductor, divided by R plus JXL, which is impedance of the whole circuit. Okay, and don't forget to multiply by initial voltage, because remember, voltage division is just a ratio problem. You're lowering the ratio of the voltage. Okay, so let's do the math together. So J8 over 6 plus J8, you're going to number crunch that, multiplied by 40, angle negative 36.89 degrees. Conveniently, this is preordained by the person who made this example, ends up being 32 angle 0 degrees, just to make life a little bit easier. And so that's our answer, right? And when we want to go back to the time domain, we just take 32, slap it in the magnitude, 0 degrees, slap it in the phase angle, bring our omega frequency with us, we're done. Okay. So you can see the general rule we're trying to show is that once you have everything in phasor form, all your basic impedance rules, KVL, KCL, resistor division, putting things in series, paralleling, all that you learned in Engineering 17 will work now. You just have to deal with imaginary numbers. And again, get this calculator. It's going to make your life a lot easier. Okay. I'll say a big caveat. Let's be real here. This works if you know how to do circuits. If you don't remember how to do KCL, KVL, you don't remember voltage division, you forgot how to do parallel and series resistors, you're dead in the water here, because this is a building, all that was a building block to this, right? So if all this I said was kind of unfamiliar, you really need to go back to your first couple of chapters in our circuit books. This voltage division, this resistor series and parallel, this needs to be second nature to you by now. This is your junior year coming in. We're fully expecting you to know this like at a blink of an eye. Okay, basic resistor stuff. Okay, phasors, I mean, it's a little trickier, but you'll get used to the imaginary numbers, but it's all a building block from that basic resistor circuit topology stuff. Okay. Now, how do we reinforce this? Remember, I talked about this in the first week. We're going to take a 20-minute break, and you're going to do this problem right now on your own. Use the rules that we just talked about, and we'll come back and we check our answers together. Okay, so let me explain what's happening. You have a voltage source. You get a single loop impedance. You have a single loop. It has four things. It has two resistors, an inductor, and a capacitor. Okay, your voltage source is 100 cosine 10,000 t plus 0 degrees. So you know 10,000 is your frequency. Vm is 100. Your phase angle is 0. So that's your voltage source. So you can put that into phasors. I would strongly suggest you convert your C and L into impedances. You have C equals 20 microfarads. You get L equals 0.5 millihenries, right? So you could convert that into impedances and then do a basic voltage division. Remember, the voltage right here is what we want across R2, okay? So we want, there's two ways you could do this. You could find the current through the whole thing and then just multiply the current by R2 and you get your voltage across. That's one way to do it. Another way to do it is you already know the voltage. You could do a voltage division with R2 compared to everything else in the circuit, right? They both will work. So you choose whichever method you want, but this is just a practice to make sure you're following the rules of phasors. Again, the hardest part about phasors, in my opinion, is the conversion. Once you get the conversion right, it's just basic impedance rules. Okay, so figure out what I1, and in this particular case, it says figure out what I1 is. So this is Ohm's law with your equivalent impedance for the whole loop. Figure out I1 of t, so you can you convert it back in time domain. Then over here, figure out V2, voltage across this resistor, and then figure out the time domain equivalent. And then we'll come back and we'll check the answers. So let's take a break. Let's come back in, let's say 20 minutes and check all your answers. Okay. So see you in a second. Good luck. Okay. Welcome back from the 20-minute break. So let's go ahead and see how this circuit problem is analyzed. So part number one is, remember, we want to try and find a current. Well, I think it's as simple as finding your Z impedance across the entire circuit, right? Now, of course, to do that, we need to convert our inductor and capacitor. So first step I would do is say J of X of C is equal to negative J over WC, where W is 10K, right? We found that from here. And the capacitor is 20 microfarads. Right, number crunch all that, you get negative J5. So just remember, capacitor is negative J5 now. Inductor, we can do the same thing. Jx of L is JWL, where you take J multiplied by 10K times 0.5 micro, which is right here. And that's positive J5. I said that's an error. I should have a J right there. Okay. We know our voltage is 100 angle 0 degrees. We got that from the initial voltage right here. You got 100 angle 0 degrees. Resistors stay the same because we don't have to convert them, and this is all our building blocks we need. So to find the current, it's just Ohm's law, V over Z, right? So we have V over Z, Z total, I'll call it. So you have 100 angle 0 degrees divided by negative J5, which is a capacitor, 2.5 ohms, which is R1, positive J5, which is inductor L, and 7.5 ohms, which is R2, right? Now, I chose inductor capacitors carefully to make our number crunching easier. These two cancel out. Notice you have a positive J5 and negative J5. When you add them together, they're going to cancel. It's really going to be 2.5 plus 7.5, which is 10. So our current is really just 10 angle 0 degrees, 100 divided by 10. Okay. We could convert that to time domain, which is 10 times cosine of 10,000 t plus 0 degrees. Okay. Now, for the second part, let's figure out the voltage. Well, we know the voltage for V2 is V1 multiplied by the voltage division, which is R2 over all impedance. right? So you remember voltage division is always the volt, you multiply by the resistor that you want the voltage across, divide by all the voltage in the series loop, right? And they multiply by the initial voltage. So it's kind of like a ratios problem. Little bit of voltage comes across R2, a lot of it gets left off of C, R1, and L, so this is a ratio problem. Now, conversely, you could have done the other way to where you multiply current times R2, which will give you the voltage. Obviously, that's the easier way. I want to do a little bit harder way just to, reinforce voltage division. So V2 is equal to initial voltage here, voltage times R2, divided by your whole impedance. We already calculated Z total from previous one. We know it's 10. We know R2 is 7.5. So 7.5 divided by 10 multiplied by initial voltage of 100, we get 75 angles 0 degrees. So V2 is going to be 75 cosine of 10,000 T plus 0 degrees. Okay. So that's pretty much how we do this version of our circuit analysis. Okay. So hopefully you got that right. If you didn't, got you some step-by-steps. Go ahead, redo it again, and try to figure it out. Okay. So moving forward, let's get to something a little bit harder, right? Let's get a circuit that's more complex, that's going to require something past just, voltage division, right? So here, notice we have a circuit with two sources. Now, the fact they have two sources, and it's going to make it a lot more complicated because you can't just smash everything in one impedance and just do a single Ohm's law. So even though it's more complicated, we still have our step process. Let's do everything we've learned, and we should be able to solve this relative ease. The first step, we have a source, this one right here. This is a current source. We know IS is equal to 10 cosine of 50,000 T with an angle 0 degrees. That's all we need to get our current source in the phasor domain. So 10 angle 0 degrees amps. Next, we have voltage. We have a voltage source right here. Actually, that was green, so let me keep color coded. Okay, we have a voltage source right here. Right? That is Vs of T is 100 cosine of 50,000 T minus 90 degrees. Okay, so don't forget the minus. So here, Vs is equal to 100 angle negative 90 degrees. And we just got that written in there. One tidbit I want to show everybody. Notice that the two circuits both have the same frequency. Okay, I don't know if no one ever told you before. In general, when you have a circuit, all the sources have to have the same frequency. You can't have a 50,000 frequency source attached to a 10,000 frequency source. They're going to fight each other and they're going to blow up. Okay. So most of the time in circuit analysis, you only have one source. Like in the lab, it's going to be that function generator. But there might be times where you have multiple sources. You have to be very careful and make sure that the two sources have the same frequency. Otherwise, they're going to fight each other and one's going to get damaged most likely. Okay. So it's common practice. If you see a source with a frequency, expect the rest of this frequency of all the other sources to be the same as well. Otherwise, I don't know what you're dealing with, right? Something a lot more advanced than what you could expect from circuits. Lastly, we have the voltage right here. We're asking what's the voltage on this leg between here and here. Okay. You gotta say what's the voltage across the capacitor or the resistor or the inductor. Really, it's the voltage across this entire leg. You won't be honest. Okay. What's that voltage? Again, that's an unknown. So let's go ahead and just label it down here in a Laplace circuit and just capitalize it to remember, hey, this is what we're looking for, capital V. Okay. So all our voltage and currents are now converted over. So that's step number one. All right. Step number two, oh, sorry. Also the impedances, we forgot about that, right? So kind of already did the number crunching for you. 9 microfarads with 50,000 radians per second. That's going to be negative J 2.22 ohms for the capacitor, 100 microhenries into 50,000 radians per second is going to give you J5 ohms for an inductor. So again, I didn't do here, but it's the same conversion process. You convert farads and henries into impedances. Okay, remember Jx of L is JWL, and then Jx of C is negative J1 over WC. Okay, you're going to memorize this by the time we're done talking with all this. All right, so we have everything converted. So this is our Laplace circuit at the bottom. Let's keep on going. So now let's talk about what type of circuit analysis we should use. Well, to be honest, this is kind of like a tailored circuit to where the most obvious one is node analysis. So notice we have one node. This is also where the voltage is. And this is the ground for it, okay? Or the negative terminal. They don't really explicitly put a ground. We could put a ground if you want, just to make your people feel happy. Put a ground right there. Okay, that's the 0. And let me draw a little better. Right, but you can put a ground anywhere. The most obvious place to put a ground is on the negative terminal, what you're asking for, or the negative terminal of the sources. That's way a lot of things are cancel out. Okay, so here, this is a ground source. I might make sure we're not confused. Let's just put the highlighted part as our node. We're going to call this node V. That's because that's the voltage we want. Now, if you remember, for node analysis, the rule is all currents flown out of the node must equal 0, or all current flown in must equal 0. I chose the outro part. So notice we have 5 currents coming out. One to the left, one going to the left, one going down to the left towards the current source, one going down through the resistor, one going down through the capacitor, one going down to inductor, and one going towards the voltage source. So it's 5 currents. They all have to equal to 0. That's what node analysis tells us. So what's the rule? Well, the current coming to the left side is going against the current source, so it's going to be negative of the current source is negative 10 ohms. No, sorry, negative 10 angle 0 degrees amps. That's the current for the first leg. The second leg is the one going down through the resistor, so that's just V divided by 5 ohms. Okay. The middle one is, so now we have the middle point with the capacitor. So current coming through the capacitor is going to be the V node reference to 0. So it's going to be V, technically it should be minus 0, but we put our ground there so we don't have to. Divide by the impedance. Notice our impedance is negative J 2.22 ohms. Second to last, we have a current going through an inductor. This is V divided by J5. And lastly, we have the current flowing towards a voltage source. Okay, so if you remember what we can do here, we already know the voltage right here. That's the voltage source. So you can figure out the current flowing through the 20 ohm by taking the positive here, subtract by negative here. There's a delta V, which is voltage across the 20 ohms, and that will be our current. So you could say V1 minus, so the voltage at the node we want, subtract by the voltage that we're going to, so V minus 100 angle negative 90 degrees, divide by the impedance. This is your basic Ohm's law, right? So this hopefully should just be bread and butter to you by now. Circuit analysis, you probably got slammed by this nonstop in Engineering 17. So we got one giant equation, okay? Couple of things to note. Note there's only one variable. It's just V. Everything else is just number crunch. Number 2, note that the inductor and capacitor are impedances. So we could treat them like they're resistors with J values. This is infinitely easier than trying to do differential equations through node analysis. Okay. So all we got to do is clean this up. Kind of did a couple shortcuts, but if I was going to do this one by one, 100 goes on the other side. So add 10 angle 0 to both sides. That's how you get this one down here. Okay. Next, I would do this part right here. Negative, technically, is this one, all this, right? that can get crunched apart because the top you can always split them apart because they're adding or subtracting out of each other. So you get negative 100 angle negative 90 degrees divided by 20, right? So we throw down another side, so we have to add the equivalent. So we're adding 5 angle negative 90. So that's how you get your two constants. Everything else should just be smashed together because there's a common V. We could pull the V out. Okay, so we're going to pull this V out. We're going to pull this V out. We're going to pull this one out. We're going to pull all the V's out, and whatever's left is the junk. So notice we have V multiplied by 1 over 5. Control Z. Okay. So we got 1 over 5 right here. Switch over this. All right, because we took the V out. We got 1 over J 2.22 right here. We took the V out there. 1 over J5, we took the V out there. And 1 over 20, we took the V out there. Don't forget that 20, it does go right there as well. Okay. So this is just a number crunch. Now, doing this by hand might be kind of hard. Common denominator, blah, 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 bull crap from middle school. Get your calculator out, just number crunch this. And then take that divided by these two added together. Your total result is going to be, sorry, these two numbers put together is 10 negative J5. This you still need crunch. And your total is going to be 10 minus J30. Okay? So, feels a little confusing. That's this number. That's this number. And then we still have all this to number crunch. Multiply by V. Okay? That probably makes it a little more. That way, no one's getting confused in the math as much. Okay, so we crunch all this together, 10 angle negative J30, that's their voltage on the main node. And that's what we wanted. Okay, so this is all arithmetic. Vectors with imaginary numbers, but again, get your calculator out like this. This should be pretty quick. Okay, so that's using node analysis. And to be honest, looking at this circuit before all that coming up here, it's not easy. Okay, give me 1 second. All right, so now let's go ahead and do circuit analysis techniques using phasors for mesh loops. Okay, so here we have a circuit with 3 loops. It's actually pretty complicated if you think about it. You have a dependent source on the right side, and this dependent source is based on the voltage across the capacitor. So unfortunately, you can't crunch all these impedances together easily because you still need to know the voltage across this capacitor. Okay. You also have another voltage source, sorry, current source. A dependent current source with the voltage across the capacitor being the dependent part. So this needs to stay apart from the rest of the circuit. You have a voltage source here feeding into the circuit through a 1 ohm and 2 J ohm inductor. Okay. So node analysis is going to kind of work, but the problem is you're going to need a second equation to figure out this voltage here. Current loop is actually easier in this part, right? Probably both of them are not the easiest, but I would do current loops. Okay. So mesh loops is what we're going to do. We want to solve for I1. So this is ultimately what we want right here. So step number 1 is you should always make the current of the loop flow with the answer you want. So if you want I1, make I1 flow with that. Okay. Another big trick is whenever you have a dependent source, it's always a good idea to make sure your current loop will flow with the current source, especially the dependent source, because then this current loop will literally just be whatever this current source is. So you could, instead of having I1, IA, or IB, we could literally say IB is equal to 0.75 Vx, so we're kind of canceling a variable out. So again, any current source, just that loop is literally that current. Okay, and then we have a middle loop, we'll just assign IA. Okay, so we have our 3 loops. Now we've got to start doing our mesh analysis. So remember 3 loops, we'll go through each one. So the first one we'll do is I1. And you remember the rules, so we're going to go clockwise. So I always start with the source. So remember, all your voltage drops across the loop must equal to 0. So they should all equal 0 at the end of the day. So current will flow into the negative terminal of the voltage source. So it should replace a negative value to the voltage. So negative 33.8 angle 0 voltage here. We're going to go and we're going to hit 1 ohm and J2 ohm. So we're going to multiply I1. I1 should be multiplied by these two impedances to find your voltage drop across these two these two elements. So you have I1 multiplied by 1 plus J2. That's to take the voltage drop across these two elements. Next, and this is where it gets a little tricky, we're going down this branch. Okay. We have a 3 ohm and a negative J5, so we can add them together. So we have 3 minus J5. But if you remember the rule, look at I1 is flowing this way. Okay. But IA is flowing against us. So whenever you try and figure out the total net current flowing through this resistor, it needs to be these two subtracted because they're fighting each other. They're flowing against each other. Okay. So you have I1 minus IA. That's where that negative came from because the current loops are fighting each other. Okay. So that's this one right there. Same thing down here. So actually, technically, the current's going to flow through both of these for I1, and they're going to flow against both of those for I. Keep that 3 in the loop like that. Okay. There you go. They're going to flow against each other for both 3 and negative J5. So then you have 3 minus J5 multiplied by the difference in current, and that all equals to 0. So their first loop is done. Now let's go to the second loop. Okay, so let's reset this. We're going to do the same thing. So here, IA is going to go through this 2 ohm resistor. So notice that we're going down the page through the 2 ohm resistor, but notice the current source is also flowing with us. Okay. So because they're both going in at the same time, do we actually add them together because they're helping each other out? So down over here, we're going to have this 2 ohm, which is right here, multiplied by IA plus 0.75 Vx. And remember, 0.75 Vx is just a current source. Okay, it's just a placeholder. So that's where you get these two numbers. And that's why we have plus. Okay. Now we're not done yet. We got to go through the other left-hand side of the loop. Remember, current will flow up through the resistor and capacitor, but we're having the I1 current fight us. So we have to do subtraction again. So here we have IA minus I, which is the first loop, multiplied by 3 minus J5, which is impedances of both of them. Okay. And with that, we completed the middle loop. Okay, remember the middle loop, it went this way. So all elements are taken care of. So that's our second equation. So notice we have I in red, IA in green, and then Vx in purple. We have 3 variables with only 2 equations, so we can't solve this yet. We need that third equation. And that's where Vx comes in. Okay, so let's reset. We don't need these current arrows anymore. Oops. Okay. So let's get rid of these things. All right. So notice we have Vx. We need to label that. Well, that's not that hard because it's already there for us. Right? Let's do green. No, let's do purple. Vx is a voltage across the capacitor. As long as you know this voltage across the capacitor, we can figure it out. Now, what's a voltage across this capacitor? Well, it's going to be whatever the current flows multiplied by negative J5. So we got negative J5 as impedance. What's the current flowing through it? Well, we got remember, we got to watch our current loops. We know we have the green current, IA, flowing up, like so. And we got the red current, I, flowing down. Okay. Now, but notice a polarity. The positive polarity is on top and the negatives on the bottom. So we have to think about the current flowing into the positive polarity is positive. The current flowing into the negative polarity is negative. So that's why we have I1 is positive minus IA. That negative IA is because this green current is flowing. I have to do it this way, but we can think about is flowing this way into the negative terminal right here. Okay, so that's why it should be negative. Okay. So here's a third equation. Vx equals negative J5I minus IA. So now we have three equations, three unknown. This is now a solvable circuit. And it looks a little messy, but you gotta remember, anytime you have a dependent source, it's always gonna be messy. But at least this is something algebra can solve. Okay. So moving down here, this is, if you take all this and rearrange it, and if you remember, with mesh loops, it's always a mess because you got to take all your I's and pull them together, all your IA's, pull them together. You can have a lot of constants in between them, and then you're going to have simultaneous equations. Okay, you got to put that standard form where you have I, right? So this is all the impedances for I, right? You got another set right here. And you got a third set right there. So that's all your coefficients for I, which was, if you recall, was that main loop this way. This is your I. Okay. Now, I did make a little change. I wrote IA for the current loop here. The answer here is I1. So if you really want to say, I'm going to write in bold, I1 is equal to IA. Okay. They just label it different. I'd rather use A instead. I like to do A, B, and C. They use 1, 2, and 3s, but it's the same logic. Okay. So now what's the coefficients for I1 or IA? It's this one, and this one. Okay. And lastly, we have Vx, which, if you remember, was a current flowing this way. Okay. And that is 0 here, so it cancels out there. 2 times 0.5 there, and -1. Okay. And then we have constants on the other side, 0, 0, and 33.8. The reason why we do this, if you remember, this is where you put in that matrix form, and then you can do simultaneous equations, hit the solve button on the matrix. Okay. So remember, all three of these came from these three equations. We're just kind of putting them all in giant rows to help us. Okay. And if you really want, you could check the answer. I should have a 1 plus J2 and a 3 minus J5 to it. 1 plus J2 plus 3 minus J5. And it's just algebra. Okay. Number crunch all this together. I mean, you could sit there and try to do it by paper and pencil. That's a hard way. Or get the graphic calculator out and number crunch it. You'll have I1 is 29 plus J2. IA, which is the middle one, is 19.4 plus J6. And Vx, which is voltage across capacitor, is -20 plus J48. All right. And the big thing is the main one we wanted was this first one right here. Right. We really just want this one. The other two are just there just to help with the calculations. Okay. But we did it. Right. Took a little math, but again, I would much rather do algebra than differential equations with dependent sources. That sounds like the biggest nightmare I could think of in undergraduate circuits. Okay, so that's kind of like showing you some of the more advanced techniques using phasors. It's the same rinse and repeat that you learned in Engineering 17. We're just adding in some imaginary numbers. That's really it. Okay, so kind of summarizing everything. Remember, for phasors to work, the circuit must all have the same frequency. I've never seen a circuit with separate frequencies, but you might, and then I'm not sure you can use phasors for that. You're gonna have to use something more advanced. Number 2, all sources need to be converted to phasors. You can't mix time domain numbers and phasors domain numbers. That's the fastest way to blow up your problem. So step 1, all sources should be converted to phasors. All voltage and current measured should be converted to phasors. Number 2 and 3, all inductors and capacitors need to be converted to phasors as well, right? The nice thing about this is all inductors, capacitors, and resistors can be treated as resistive impedances with ohms. You can reduce them like resistors in DC circuit analysis. Series resistors combination, parallel resistors. Oh, you could do delta to Y transformation, and Thevenin's Norton equivalent. All that can be done. You're just playing with imaginary numbers now. Okay. Now, here's some caveats. Because you're using vectors, imaginary numbers, you got to keep track of those numbers. Okay. You can't just throw away phase angle. One of the most common mistakes is your number crunching everything. And when you convert from a 50 plus J 30, and you just write 80. Well, it's not gonna be 80, it's gonna be like 60. Okay. And you forget that phase angle, and then you just keep going with the problem, you blew up the problem. You can't just throw away phase angles and forget it. It's critical to the solving the circuit. All DC circuit analysis or techniques are valid with phasors and circuit analysis. So source transformation, source swapping, right? What is that called? Super mesh, super node, Thorne's equivalent, Norton's equivalent. I'm missing one other. So I said source transformation, right? And KBL, KCL, and all that other stuff, right? I'm sure there's a couple kind of rogue ones that we never use, but technically all of them are useful or can be used. You must always you must be all in phasers or none. You can't again mix and match half time domain, half phasers. Okay, it's either ignore phasers or go all the way in deep into it. Okay. And honestly, most of the time, you're not going to need to convert back to the time domain. Typically, especially in the power industry, we do everything in phasers and we stick to phasers for the whole entire career. I very rarely do I go back to time domain equivalent stuff. Power electronics and electronics, you probably will be swapping more often than not. But again, it's not that hard to go back and forth, right? You're just pulling numbers out to cosines. Okay. So yeah, that's kind of our quick review slash new material, depending on who your circuits teacher was, on phasers. Okay, so remember there's a quiz and a homework for all this. Go ahead and give it your best shot. Again, you got 99 tries and all that stuff. Got any questions, let me know. Other than that, practice makes perfect, this type of stuff. Especially if you're going to be in the power industry, you're going to have to know this for the next 40 years. So I strongly suggest you learn this and get really good at it and don't just blow it off. Okay, we're going to be using this more and more, especially for the next month or so. Okay, so thank you for your time. I hope you guys have a good week and we'll catch you next week. See you around.